Hello everyone, welcome to the second lecture of week 8 on the topic of dynamic programming. Today we will be looking at a slightly more difficult problem than the coin change problem, and we will see how dynamic programming provides an efficient solution. This is an example problem from the textbook. Sterling Enterprises buys long steel rods and cuts them into shorter ones, then sells them. Note that cutting does not cost anything. Rod lengths are always an integral number of inches, 1 inch, 2 inch, etc. The price of a rod with a particular length is reflected by its market demands. So the price is not linearly related to the length of a rod. Shorter rods may sell for a higher price than longer rods. Now the question is, how should Sterling Enterprises cut a long rod into smaller pieces so they can sell them to maximize the revenue? This is an optimization problem, and dynamic programming is typically used to solve optimization problems. Now let's formalize rod cutting problem. We have a rod of length n inches, and there is a price table provided for us. In this table, it shows the price of a rod with various lengths. In order to maximize the revenue Rn, we need to decide how many pieces to cut and where to cut. For instance, if the total length n is 4, we know we can cut it as one piece with length 1 plus another piece with length 3. Or we can cut it into 2 pieces, both of which are of length 2. Or we do not cut it at all and sell it as a whole piece of length 4. By a quick inspection, we know we should cut it into two 2-inch pieces. Then we'll have the maximum revenue of 10. If the total length is 10, we should not cut it at all and just sell it as a whole for a max revenue of 30. Before we try anything smart, let's see if there is a brute force algorithm. There are a finite number of possible ways to cut the rod, so we can for sure enumerate all the cutting possibilities and compute their revenue. Given a rod of length n, there are n-1 possible positions to cut. At each position, we either cut it or not cut it. So in total, there are 2 to the power of n-1 different possible ways to cut a rod. So the brute force algorithm takes big O of 2 to the power of n complexity. So this is an exponential algorithm, not efficient at all. Now let's see if we can use a dynamic programming algorithm to solve it. In order to design a dynamic programming solution, we need to first identify a recurrence relation. How can we decompose the problem into smaller subproblems, such that the optimal solutions to the subproblems also contribute to the optimal solution to the original problem? To reduce the original problem to smaller subproblems, we can look at where we perform the first cut. We denote each possible cut position based on its distance in inches from the left end of the rod. So we say, this is the first position, this is the second, this is the third, this is the fourth. For this example here, there are 4 possible places where we do the first cut: at position 1, at position 2, at position 3, or at position 4, which means we don't cut it at all. So here is our decomposition. We treat cutting as a sequential process starting from the left end of the rod to the right end. So when we have a rod that can be arbitrarily long, we can see this process as a sequential process of finding positions to cut And this process starts from the left end, goes to the right end. That is, after we decide the first cut at position I, only the right-hand remainder of length n minus I can be further divided. The original problem can be decomposed into 4 subproblems for our example here, based on where the first cut is. We use Pi to denote the price of a rod with the length I, and Ri is the max revenue of cutting and selling a rod of total length I. So the original problem R4 now is the max of 4 subproblem solutions. P1 plus R3 corresponds to when the first cut is at position 1. The second subproblem is P2 plus R2. This corresponds to when the first cut is at position 2, and so on. Once this is clear, we can generalize this recurrence relation to a rod of total length n. Please pause the video and make sure that this is clear to you. With that recurrence, it will not be very hard for us to figure out a recursive algorithm cut rod. Given a rod of total length n and a price table where Pi denotes the price of rods with various lengths, cut rod algorithm works like this. The base case is when n is 0, there's no cutting and the revenue is also 0. When n is greater than 0, we can decompose the problem of size n into n subproblems based on where the first cut is. We can solve this problem of size n by solving these n subproblems, and then the final solution will be the one with the maximum revenue. So what's the complexity of this algorithm? The execution of the recursive algorithm is essentially the construction process of this decision tree. Again, each edge is a decision on where to cut first. Then a problem is reduced to a smaller subproblem. The recursion ends only when a branch reaches the base case, a value 0. There are 2 to the power of n minus 1 leaves in such a decision tree, so there are 2 to the power of n minus 1 recursive calls. Therefore, the recursive algorithm has a complexity of big O of 2 to the power of n. It is not any better than the brute force algorithm. However, we do notice that many subproblems overlap. If we only compute a unique subproblem once, we can avoid a lot of the repetitive computing later. Perhaps that will save us some time. Let's see. So, computing a unique subproblem only once and saving its result for future references. This is dynamic programming, as we discussed in the previous lecture. Now let's just organize our thoughts a bit and see if we can come up with a dynamic programming algorithm for the rod cutting problem. First, this problem can be decomposed in a recursive way. We have found that recurrence relation already. Second, we notice that some subproblems overlap. So how can we arrange for each subproblem to be solved only once? How can we save the solution to each subproblem when first seen? How can we look it up later when a subproblem shows up again? Please pause the video and think about this for a moment before we reveal the algorithm. So similar to the coin change problem we saw before, we can use a list R to store the result of a problem with an input I. For instance, if the total length is 10, we compute R0 all the way to R10. So we're going to use this recurrence relation to figure out all the R values. We start from R0, which is the base case. Now for R1, there is only one option, P1 plus R0, which is 1. Now for R2. There are two options, P1 plus R1 and P2 plus R0. We can compute these two options. So this one will be 2 and this one will be 5. So we choose the maximum one, that'll be 5. Now for R3. There are three options, P1 plus R2, P2 plus R1, and P3 plus R0. So we can compute this. That's 1 plus 5. This one is 5 plus 1. This one is 8 plus 0. So we know the maximum one is this, and R3 will be 8. And so on. Please pause the video and fill the rest of the table. The DP algorithm for the rod cutting problem should now be clear to you. We let R0 to be 0, the base case, then we can use a for loop to compute each element of R. Inside such a for loop, we use another for loop. To write the options, we return the last item Rn as the final solution to the original problem. Now, what's the complexity of this algorithm? This should be straightforward now. There is a nested for loop, and both the outer and inner loops iterate at most n times. Therefore, the complexity of this DP algorithm is big O of n squared. Comparing with the exponential recursive algorithm, this DP algorithm has a significant improvement. Now you may wonder, the algorithm only tells us the max revenue. What if we also want to know the detail of the final solution, that is, how to cut a rod of length n? Now let's see if we can modify the algorithm such that the detail of the solution can be saved as well. We use another list S to save the information of where the first cuts are. Sj is initialized as 0. Here, out of the J options, we use Sj to save which option has the max revenue. This also means where the first cut should be for the subproblem Rj. When we save all the first cuts, we're essentially saving all the cuts that lead to the optimal solution. For instance, when the rod has a length of 10, the first cut of the optimal solution is at 10, which means we don't cut it at all. Another example, when the rod has a length of 9. We check the table, we see the first cut is at position 3, and then we have 6 left. We check 6, that's at position 6. So it means that we don't cut the rest of the rod at all. So please pause the video and try another example. Let's say n is 7 or n is 5, and see if you can figure out where the cuts should be. After 2 case studies, now let's summarize when and how we use dynamic programming. The idea is to construct a table to save solutions to all subproblems. First, we need to characterize the structure of an optimal solution and identify the recurrence relation. Then we define a base case or base cases and compute the solutions to all subproblems in a bottom-up fashion. The last element of the table is usually the solution to the original and entire problem. You may also notice that dynamic programming uses less time by avoiding recomputing previously seen subproblems, but it uses more memory space in order to store all subproblems solutions. So this is a time-memory trade-off. You may also notice some resemblance between dynamic programming and divide and conquer. Both strategies partition the original problem into disjoint subproblems and then combine their solutions to solve the original problem. Their difference is that Divide and conquer solves every subproblem at every occurrence, even repetitive ones. On the other hand, dynamic programming solves each subproblem only once and saves its answer in a table. Such a table can be quickly referenced to when the same subproblem occurs again. You may find it helpful and revisit some of the problems we discussed before using divide and conquer and compare them with DP algorithms to see their differences. There is a chapter in the textbook dedicated to the rod cutting problem. There's some exercise questions that come with it. You may find these exercise problems useful. Okay, that will be all for the second lecture of this week. I will see you in the third lecture on dynamic programming. Stay tuned.